Okay, hey class. Let's go over these notes, data graphing, and visualization. All right, so here we go. In this section, we will discuss the importance of displaying data in an appropriate manner. More often than not, it's easier to understand data when it's presented in a way that's visual. So, probably many of you experience this. It's just a lot easier to process pictures for most people than it is just sort of tables and tables of raw numbers. So we need to sort of just realize that and realize that if we're trying to communicate with statistics, especially this idea of descriptive statistics, where we're just trying to describe, a big set of data in some way, a real powerful tool and one that's very useful, again, if we're trying to communicate with this, is with some kind of data graphing, visualizations, and charts and that types of stuff. And also, we have to learn some of this stuff because it helps us later on in a few weeks, to really understand distributions. In fact, this first topic we're going to talk about is called histograms. Histograms is something you've probably seen and probably sort of heard about before. So it says here it's a pictorial representation of the frequency distribution of the data. Oh, great. And shows how the values of the data are distributed. Again, this sentence isn't that great. A frequency distribution is a tabular summary of the data. A table is obtained by grouping data into categories or bins. So here's an example. So pretend like you're a manager from a small pizza parlor, and you're thinking about giving a money-back guarantee for anybody who has their pizza delivered after 30 minutes after it's ordered. So you collect a bunch of data on over lots of days and hours on how long it took to get a pizza delivered, and then you just recorded those, and here it is. So here's the data, very useful. Total time after initial order to pizza receipt. So these are all in minutes. So what do you think? There's a bunch of numbers. Great. So, one of the first classes we talked about this fact that sometimes we just have lots of data sitting around. Here's an example of just data sitting around. What should we do with this? Is the question. First of all, we have to sort of think about, well, what is it we want to know? Well, we want to know whether or not this money-back guarantee thing is the right idea. If it's a good idea, I should say. So we think about that. How do we determine that? How do we know if it's a good idea? Well, we could look at all this data and just see how many of them were more than 30 minutes. In fact, that's what we're going to do. So what a histogram does, though, in particular, is that it will sort of take a look at all this data. This is all continuous data, right, as opposed to discrete data. Remember, discrete data is sort of chunks. Continuous data is a measurement sort of across an entire scale. What histograms do then is sort of take continuous data like this and chunk it up, make it sort of discrete in some sense, discretize it, and then count how many times we see something within each discrete segment. The discrete segments are just sort of what we call bins, smaller ranges, right? So in this case, we might have a range, between 20 and 21 minutes, between 21 and 22 minutes, between 22 and 23 minutes, between 23 and 24 minutes. So these bins then are just sort of discretizing, chunking this up, and then we're just going to count how many times we see an observation in each of these bins. And then we're just going to visually display that. That's what a histogram is. Visually display sort of the frequency of how often we see things in each bin. So let's go to the next page. So clearly this is sort of hard to interpret. So we could come up with a frequency distribution that looks like this. We say, what if we make a chunk between 16.9 minutes and 18.84 minutes? Well, it turns out there's actually 3 pizzas that were delivered between those two. And if we go between 18.84 and 20.78, there's 13. Between 20.78 and between 22.72, there's 38 pizzas, and so on and so on. All right? So over here, we have the frequency, how often the pizza showed up. And over here, we have the bin sizes, the range of the bins. So these bins should be the same size, the same width. Not the same height, right? Because the frequency is going to say how tall it is. But they should be the same width, meaning... in this case, it looks like they're all just about, just a little bit less than 1 pizza, 1 minute away from one another. From 16.9 to 16.84 is almost 1 And you can see that it follows that same pattern all the way through. That's important, that they're all the same size. So Excel, when we do this in Microsoft Excel, it will just create the bins for us. So we don't have to really, there is kind of a bit of a science and some algorithms to sort of figure out how to make these bins. So sometimes we want to make the bins in a way that makes sense. In fact, I think because these are so close to 1 away, I think it might be smart, in fact, to just say, well, why are we doing 16.9? Why don't we just do 17? Or 16, between 16 and 17, between 17 and 18, to make whole numbers. And that's okay too. So we can make our own bins if it makes sense. Excel will make them for us though. Let's see what this looks like in a histogram, actually a picture, a histogram. This is a histogram. So let's talk about this. Along this axis over here, this is time, right? So this is our measurement. So the x-axis will always be sort of a measurement. In this case, it's time to deliver pizza, right? It's what it is we measured. Deliver pizza. So you can see over here, it looks like our smallest one, was something less than 17.89, and then as we go across here, we have sort of more and more and more. This is the frequency. So how often do we see a pizza? So this is like 1, 2, 10 pizzas right here, 20 pizzas, 30, 40, 50, the number of times we see that. So then we end up with sort of some kind of shape here, all right? You can see the shape looks kind of like this. All right, so a few things here. We see that this is actually what we call positively skewed. Positively skewed. Which just means that it sort of skews off to a positive direction. Skews just means it's sort of the hill, the slide goes off to a positive direction. We can have a negatively skewed. We'll talk about that in a little bit. So again, back to our original question, is 30 minutes the right thing? So let's go take a look. See, 30 minutes is something like right around here somewhere, looks like. And so we would say everything over here, this whole area right here, this is pizza is free. So then I would ask, if I had you in class right now, I'd say, well, do you think that's a good idea? And somebody would say, well, it's not too bad. But somebody in class would say, you know what, it's not terrible, but if you just draw the line right here at 35 minutes, it's only 5 minutes more, you're not going to give away hardly any pizza. And that makes actually a lot of sense, right? So right away, we can see that there's value in what we just did in making this histogram, is because we can see right away that there's very few that are way out here. There were still quite a few between 30 and 35. But we could, I don't think anybody would, consumers would say, well, 35 minutes, that's terrible. Oh, no, let's just do 35 minutes. It's fine. So let's make it at 35 minutes. We probably wouldn't have known that if we just looked at the raw data. So that's one thing about the histograms that can really sort of benefit decision makers. So, all right. So what did we learn about the? This is really what I wrote down up above, so you could write it down again or right there if you'd like. So how do we do this in a spreadsheet? So we'll do this in just a minute. Let's just keep going through the notes. But we do this with a data analysis add-in. So we'll do this in just a few minutes, or maybe I'll make sort of a whole separate video on that just so that it can be separate. But once it's made, here's the output we're going to see. So Excel will make this output. It won't always have this cumulative percentage guy over here unless we ask for it. But it will certainly have a bin and a frequency. So what do these bins mean? Well, let's talk about that. So down at the bottom of this guy, we're going to scroll out just a little bit. It's going to ask some interpretation of these numbers. What's this bin labeled 16.9? So it's saying, what is this guy? What is this frequency of 16.9? Well, what that means is that, oh, I'm going to sneeze. Excuse me. All right. It means that, let's see, at least, one observation, in this case pizza, observation is less than or equal to 16.9. Less than or equal to 16. I just want to make sure I got that right. Yeah, that's right. At least one observation is less than or equal to 16.9. All right. Great. So what's the next question? This question is, with spin label 22.72. Let's look at that guy. So we got a 38 right here. What does that 38 mean? 22.72. Well, that means is that there are 38 observations, 38 pizzas, in between that are greater than 20.78 and less than or equal to 22.72. Greater than the one above it and less than or equal to the one below it. So it could actually equal 22.72, but it's in between these two. That's really what it means, including this one. So let's just write that down. What was the number? 20.78. 20.78. Oh, I forgot the number already. 38. So this means there are 38 observations, pizzas in this case, observations between 20, I've forgotten already what it is, 20.38 or something like that, and 22.72, right? 38 observations. Okay. What about this bin labeled more? Well, it just means there's more. More than what? More, there's at least one more than 44.06, right? More than whatever one's right above it. So there is one observation greater than 40, I've forgotten already what it is, sorry. 44.06. 44.06. All right, interesting. So that's what's going on. So you'll need to be able to interpret a frequency diagram, no doubt. So, in the exam, there's usually a question that says something like, all right, well, tell me how many, however many somethings are between, 30.48 and 32.42. So the number is 8 with that question. It's not 18. You got to figure out if I say between 30.48 and 32.42, it's that one, 8. 18, what is that? Well, that's between 28.54 and 30.48. All right, so we just got to make sure we understand that. Great. So the cumulative percentage then, again, this is something we have to ask for, and I don't generally always do that. But it just gives us sort of the ongoing running percentage of how much is actually there. So that's kind of useful sometimes because it says, how much has happened already. So if I say at 20.78, there are 6.67% of all the data is sort of less than or equal to 20.78. So I could go over here and say 90% of the pizza is actually less than 30 minutes, 90%. So that means if we do the 30-minute thing, we're going to give away, 10% of all our pizzas. If we go over here to 35, which we don't have a full 35, but at 34.36, we're now at 97.5. So my guess is that if we put the rule at 35 minutes, we're going to give away, roughly 3% of all of our pizza, which is easier to swallow than 10%, right? So again, this sort of cumulative percentage is useful. All right, done with that page. We'll talk about this when we get into the Excel, but there's some things that we have to change. Actually, we'll talk about this right now. So this very first bin, remember, Excel is going to make these bins for us. When Excel makes it, it always makes this very first bin always have a frequency of 1, which doesn't make a whole lot of sense. But you could just delete this 1 and put it down here and make this 2 a 3, right? And then just get rid of this whole row right here, 3. We have to add these two numbers together, but then leave this as 18.84, and it would be the same, right? It would really be, because the interpretation is, well, anything less than or equal to 18.84 would be 3. So I typically do that when I make a histogram. The other thing is that histograms look very similar to bar charts, which is, we're going to talk about those in a little bit, but they're not quite. So bar charts are really sort of sometimes measuring counts or means or some other things of discrete things, whereas histograms has a continuous axis on one side that has become discretized, that has some kind of created chunks. So in order to continue to think about sort of the continuous nature of the data that was collected, there's usually not gaps in between the bars on a histogram. So Excel makes gaps, though, automatically. So you have to go in there and sort of tell it to stop making gaps every time. So that's the other sort of fix in Excel. So we'll do that in another video. It's not too hard. Okay. So let's talk about different types of shapes of histograms. So a symmetric shape is one that is sort of the same on both sides. Whoops, that one is not very good. But pretend it is. So, wow, yeah, just not very good. Just pretend that this looks the same on both sides of this line. So that's what symmetric means. So a bell-shaped distribution is symmetric. Let's see, another one would sort of be something like this. All right, so that's also a distribution shape, a histogram shape. But it's also symmetric, right? Because I can cut it down right straight down the middle and fold it in half. It looks the same on both sides. So symmetric distributions come in handy because we only actually need to know half of what the distribution looks like, and then we know what the other half looks like. They're the same on both halves. So that's good. Skewed distributions, there was a couple videos about skewness that you were supposed to go watch. If you haven't seen those, you should go check them out. But skewness is something like this, right? I have something that starts big and then slides off away over here. Or it could look over the other direction, right, where it kind of has a really long taper and then comes up and then comes sort of back down or something like this. This over here would be a positive skew. That's a plus sign, positive skew. This would be a negative skew. All right, so somebody might say, well, the data's great, but it's got a negative skew to it, or it's positively skewed. All that really means is that it's going in one direction. There's more observations out here than there are on the other side. Or a negative skew means that there are more on the left side than there are on the right side. That's all it really means, right? So that's it. Unimodal versus bimodal. So this modal thing, this has this word mode kind of as the root. Remember, the mode just means, what does the mode mean? The mode means the one that happens the most often, right? So unimodal and bimodal just means, is there something that sort of is more likely to tend to happen more often? So here, let's draw a couple of these. So a unimodal distribution would be something that just has sort of one hump like that, whereas a bimodal would say, well, it actually has two little humps like that. Like, so there's two places where it might kind of have a little peak or something like that, so we would call that bimodal. In fact, that could be more than two, and then we would call it multimodal, right? So there's multiple modes is really what that thing is. Unimodal means, well, there's really only one mode, a single mode, unimodal. All right, so here's a stupid little picture of a little bum sitting on the street, and he looks up on the wall, and there's a distribution, and he sees here the little X says you are here. So this is supposed to be probably a distribution of, I don't know, income or prosperity or something like that, and he's on the lower tail. This is supposed to be funny, and usually no one laughs in class. So if you're not laughing right now, you're doing really well in my class, so that's good. If you are laughing, I'm sorry. All right, so box plots. Another way to summarize data then is to look at box plots. So box plot shows extreme values of the data and the quartiles. So here's an example. So here's a box plot. Along this axis, again, is the measurement. So here would be like time. This is a bad plot because it wasn't, the axes were not labeled. So you should always label your axes. So this is time. This is our continuous sort of measurement that's going across. This line right smack dab in the middle of the box plot, this is the median. This line over here going up and down is, let's see, this one right here. This one right here is the first quartile. Oh, first, that's supposed to be a number one. First, it's getting worse. Try again. First quartile. Yeah, there we go. First quartile. The one on the other end of the box is the third quartile. What's a quartile again? Quartile is, the first quartile is the 25th percentile. The third quartile is the 75th percentile. And the median, we say, is the 50th percentile. 50th percentile just means half of the data is on one side and half the data is on the other side. So the distance between the first and third quartile represents 50% of all the data, and we call that distance the range between here and here. We call that the interquartile range. Remember that? From here to here. This is the interquartile range. It's just the third quartile minus the first quartile, the distance between those two. So this box plot is a way to just visually see what's going on real fast. And whenever you see a box plot, know that the box, whatever you see in the box, that represents 50% of all the data. which is pretty cool, right? So we say, well, half of all pizza deliveries are between, it looks like, I don't know, what's that, 20-something, 21 or 22, and 28 or something like that, right? So that's cool. And then we see these guys over here are called whiskers, the little things that point out on the end. And there's different rules about how to do the whiskers, and I have a couple of videos about how to do this. We're never going to really make one of these for this class, but it does come in handy to look at these. And the dots, the circles, are generally kind of like what we call outliers, something that are a little bit bigger. And I think the rule of thumb is something like an outlier is a couple distances past the interquartile range or something. I can't remember. I made a video once so that I could immediately forget it. But it's in a book and it's in a video, so if we ever need to look it up, we can do that. But the way to think about this is that there's actually quite a few. You could look at this and say, well, there's quite a few kind of big ones out here, some big outliers. And so that would scare me. Again, if I was giving rid of pizza at 30 minutes right here, I'd say, well, look at all those. There's lots of guys over there. But if I was at 35 minutes, that's like right about here. Again, I'd say, well, there's fewer over there, so that's not so bad. The great thing about box plots actually is when you're comparing multiple discrete things with box plots. So it could be that we own 4 or 5 stores. And then what we do is we do this same box and whisker plot for all 4 and 5 stores, and we put it on the same chart. And that way we can immediately visually see if one store is doing better or worse than another one, right? So that's actually really powerful and really cool. And in fact, it actually leads us, when we get into inferential statistics, to really understand a lot about how to compare different things with one another. It's essentially doing the same thing. Okay. All right. So that's box plots. There's no add-ins, there's no way to do this in Excel real easy. There are some add-ins, and then I've made a couple of videos. I've actually figured out how to do it in Excel, but it's sort of like standing on your head and doing weird things. So we're not going to force ourselves to do it in this class, but if you'd like to do it, there are some videos on the website on how to do that. Here's a little comic. Can my boyfriend come along? I'm not your boyfriend. You totally are. I'm casually dating a number of people. She displays a box plot. But you spend twice as much time with me as with anyone else. I'm a clear outlier. Here she is out here. The amount of time. This axis must be the amount of time you spend with people. Something like that. Your math is irrefutable. Face it, I'm your statistically significant other. I'm telling you, statistics humor, it just doesn't get a lot better than that. All right, so what else can we do with displaying data? So pie charts. Pie charts show up a lot. So there's some rules of pie charts. Actually, I'm going to show you some really bad pie charts, and then I might show you some good ones. So here's my first rule. Proportions must equal 100%. So this is kind of an old chart, a couple years old, depending on when you're watching this video. Maybe it's really old. But here was a question. Fox News said, well, who would you back, given these different political opponents that were trying to run for the Republican presidential bid, GOP candidates? As you can see, these percentages, they're really great. The problem is it does not equal 100%. That's a problem, Fox News. So, so when you do a pie chart, it has to, all the proportions have to sum up to 100. The reason this happened, and maybe some of you figured this out, is that people actually might back all 3 of these, right? In which case they'd say, yeah, I'll back all 3 of those. That's fine. It's okay to ask that question and okay to allow that to happen. But you can't make a pie chart out of it, right? So here's another one. It's kind of the same problem. This is actually, I really love this chart. It's a pie chart about pie. I mean, who thought of, that's beautiful. It's great. So they asked this question, what's your 3 most favorite types of pie? The problem is this 3 here. Yeah, we shouldn't have asked 3 because it does the same problem. It's because now no longer can we sum up to 100. It's fine to ask that question, but you can't make a pie chart out of it. Even if the study is about pies, you just can't do it. So anyway, so that's great. So that's a rule. I don't like 3D, and the reason why I don't really like 3D in anything at all, but the one main reason is that this guy over here on the very front is always going to look bigger than anything on the back. So you could be deceptive here. You could say, well, the one that I want to look bigger, I'll just move him over here, shift him to the front, and then he'll just look bigger. Right, so 3D, just stay away from it. It's not really that cool. So anyway, that's that. Final rule, don't use pie charts, especially when bar charts will look better. So there's just a few examples of the exact same data in pie charts. Lots of stuff going on here. Actually, pretty hard to really know what's really happening. In fact, so this one right here, it says it's 14.17%. I think that's that color, right? Which is a little weird. I don't quite get it, because here's another one right here that's like the light green, which I think is this one, which is, it says it's 18%. It just doesn't make sense. Like something goofy's going on. We take the same data over here, get rid of the colors, just make bar charts going across. This one is probably appropriate. I think these all sum up to 100. That's okay, but so what? Let's make bar charts, and immediately you can see, well, here's the big ones, and then we scroll it down to the small ones. You can see that it makes much better sense. Same kind of problem here. This pie chart is just way too busy. A lot too much going on here. It's really hard to visually see what's happening. There's actually, so each of these colors have two different shades of colors, because it's two different types of purchasers or something like that. One's consumers and one's a producer or something like that. So you can do the same thing with bar charts. In fact, this, again, get rid of all the colors. We just have two shades of black, and it does the same thing, right? So it's actually way easier visual to see what's going on. Again, all right. So here's a bar chart. We talked about bar charts already. So remember, bar charts is where we sort of find these discrete things and then maybe find a count, frequency of how often it is. So here's dangers indexed by the number of Google results for died in a blank accident. So we have the number of people over here and then the type of accident. We have blogging accident down here. There's 2 people who has died in a blogging accident. So that's too bad. Here's a question. Can you make this into a pie chart? Can you make this into a pie chart? The answer is, well, yeah. Should you make it into a bar chart? Well, I'm going to go ahead and say no. The reason why is because this actually isn't all possible things that you could possibly die of. And so why are we making this into a percentage? I mean, remember, a pie chart is always kind of some proportion of percentage of something. So unless you're talking about a whole of something, then why are we breaking it up into percentages? So unless we maybe say, well, this is all possible ways to die in an accident, then we can make a pie chart. But it's not. I mean, there's got to be some other things in there. So I'd say no. What's the difference between a bar chart and a histogram? We already talked about this. Histogram is really about, has a continuous axis. Continuous axis. Broken into bins. Broken into bins. Where a bar chart is usually just discrete things. I don't know, it's like discrete categories. How about that? Categories. Yeah, it's kind of a little bit, they're really very similar. I mean, they're kind of like cousins or something, because when we break things into bins, we're sort of, like I said, discretizing them. The difference is that we still have a continuous axis. We're still treating it as if it was a continuous axis down the bottom, where a bar chart is not. Histogram, you probably shouldn't move the bins around. Where a bar chart, you could. I mean, you can sort things around. That's not a problem at all. All right, what's next? Line graphs. So line graphs are generally used to display the change of a variable over time, with time as the x-axis and the measurable continuous variable on the y-axis. So here on this one, we have time on the x-axis. So the line chart almost always has time. And then the variable that we're actually tracking over time is called my overall health. And here's our line for the line chart. So here's my overall health. Seems to be puttering along. And then at some point, it just takes a nosedive. And then here, this comes down here and tells us that that point was the day I realized I could cook bacon. I could cook bacon whenever I wanted. So then overall health just took a nosedive. So, all right. This one's kind of goofy. Let's not look at that one. All right. So the last one then is scatter plots. Scatter plots. So we've already talked about scatter plots when we talked about correlation. The idea of scatter plots is here, so I'm taking 2 measurements of the same thing, different types of measurements of the same thing, right? Yeah, so this happens all the time. In fact, with our M&M bags, remember we measured the weight and the count of M&Ms, and like the count of each color, all kinds of things, right? So there's no problem in measuring multiple things, measuring the same thing multiple times in different dimensions, essentially. So scatterplot allows us to visually see 2 dimensions, right? 2 dimensions over time. So here's a kind of a fun one that I found online. So here's all the points here are different fruits, and this dimension is tastiness. tastiness. So down here we have untasty, up here we have tasty. And then this x-axis is difficulty. So it's very easy to eat this, I guess, and very difficult to eat this. So over here, closer to difficult, we have like pineapples and pomegranates and grapefruits. Kind of difficult to get at. Oranges are less difficult, but kind of difficult. And then, still a little bit on the left side of difficult, we have watermelons and lemons. I'm not sure. Lemons, I don't know. And then the tastiness scale, up here on the very, very tasty, this person, whoever made this, really likes peaches and grapes and pineapples, it looks like. And is not a big fan of lemons and grapefruits and tomatoes, right? So they're down here on the untastiness. So perhaps like the best quadrant to be in, if you want to think about it, is sort of the tasty, easy quadrant. So here we have seedless grapes, strawberries, blueberries, pears, looks like green apples, peaches. All right, so that's kind of an interesting way to think about it, or to display 2 dimensions of data. All right, final thing. So this comes out of the textbook, but there are 5 things that tend to come up in good charts. So large sets of data that represent that are represented simply and coherently. The chart can stand alone to describe a story, so it replaces words. What that means is oftentimes we have to make sure it's very clear what's going on, axes are in there, but you could just display it and then just talk about it. All right, 2 or more variables are compared. So what we just talked about, a scatter plot, is a great way to have 2 or more variables compared. Time, a line chart has time over some variable over time. Substance trumps form, so don't make it so pretty like 3D. No, if pie charts that are just too busy. No, make it so that we can actually see what's going on, and then there's no distortion. Again, the 3D sort of distorts things, and there's other ways to make distort stuff. All right, so in class I sometimes talk about this this chart, kind of a famous chart of Napoleon's march into Moscow. So this was during the War of 1812. So Napoleon takes a really large army and marches kind of through winter into Moscow, and here's a visual representation of that march. And what we see here is this brown picture is Moscow's troops heading towards Moscow. This is actually a map right here. So underneath we see a map. So there's like some rivers here, Moscow's right here. It's in French, so I can't really tell you what else is going on here. Here's another river. So when he crosses this river, the relative size of this brown thing is how big the army is. So it actually shrinks, right? So as it gets smaller, the army gets smaller and smaller and smaller and smaller. And the problem here is they're not doing so well on the way to Moscow, as you can see. So they get sick. There's some pretty bad weather. They leave people behind and some other stuff that's just not going so well for them. By the time they get to Moscow, they're actually just a fraction of what they were before. And they lose a battle with Moscow, with Russia. And they have to retreat. This is actually, I think, one of Napoleon's first defeats, and it's sort of the beginning of his decline. So up until this point, he just never lost. But War of 1812, he lost. So he's coming back. So the black line then is his retreat, the retreat of Moscow. And again, the size of the black line represents how big the army was. So you can see that, he leaves Moscow about the same size as he got there. I mean, a little smaller. And then, on his march back, loses a lot. By the time he gets back, there's just really, really very few people left. So down here then is the temperature going on during the march. So I guess the thing that makes this chart a little bit famous is that it represents lots of different dimensions, different variables, all in one chart. So we have a map, we have the size of the army, we have the direction of the army, we have the temperature at some point. And we also know whether they actually were going or coming based off of just 2 different colors, which is pretty simple and pretty easy. So again, we can tell a lot from some charts and graphs and stuff like that. So it's something that we need to really consider using pretty well and figure out how to use them as best as we can. All right, so that's it for these sets of notes. And I'll make a little video on a histogram, and then I think we'll be done with this unit. All right, thanks.